So we've kind of hinted a lot about stress fields around dislocations, but let's actually get quantitative here for edge and screw dislocations for isotropic linear elastic materials. So let's think about a straight infinite edge dislocation with the tangent vector along the positive z-axis, or the 3-axis here. And we can also think about the Burgers vector along the positive x direction as well. So if those conditions are met, we can describe the stress of our edge dislocation as follows. So we can see in the stress tensor, that tangent vector, again, along the 3 direction, our Burgers vector along the 1x direction, we can see we have a combination of some normal forces, and we also have some shear stress values as well. But every other component here is going to be 0. So we can actually look and visualize what this looks like. So we can look at this edge dislocation, we can plot it. So for along the sig xx values, you see it makes sense. Compression at the top, tension at the bottom. You can also see shear stress values. You can also see in the ZZ direction. Again, it looks like some orbitals and crazy artwork, sig xy. And you have essentially your edge stress tensor. So that's what effectively it would look like here. So we can do and derive something very similar for a screw dislocation. So again, a screw dislocation with its tangent vector along the positive z-axis, its Burgers vector right-hand screw also along the positive z-axis, and we can derive and figure out and look at the strain once that step is left behind. Once that Burgers vector basically propagates along that line direction in the material. And we can see our shear stresses, and you can see here, we only have shear stresses. This is very, very impactful. All other components are 0, so there are no normal stresses here. This is going to be very, very important. It's a very interesting finding a little bit later when we talk about interactions with those defects. So for screw defects, we're in pure shear. Edge defects, we have both shear and normal stress components. So that's going to be very, very important. We can also calculate the energy of dislocations as well. So we've kind of looked at this previously, and again, we can actually visualize before we move on here. Let's look at our, again, screw stresses. You can look at sig xy. Oh, we need to sig xy(s) for screws. Let's type that in. And that makes sense. Compression at the top, again, you can see those values. You can see ys. And again, our little orbitals and values. You see that white basically at the origin. That's basically a singularity, and infinite values. Anyways, we can look at dislocation energies as well. So we can use that following relationship. We can calculate the energy of a screw dislocation, and you can see the energy per length is proportional to your shear modulus, your Burgers vector squared, and again, if your R approaches R naught, you get an infinite value, and the same thing, or a singularity there. So infinite once that dislocation becomes very large, effectively. So you can calculate those values here, and next time we're going to see how these dislocations interact with point defects. Specifically, how do they interact with vacancies? How do they interact with interstitials?